I still get excited about missing the record button, so I just want to get going and teaching. Okay, so we're going to do this one. We're going to break our convention in this one just to show you what's going to happen. Like I said, normally you're going to just want to go clockwise. That's how everything is set up in the answers for the quizzes. Everything's assuming you're going clockwise, not going the other direction. So, first thing we need to do is we're going to look at loop A and then loop B. We're going to write out our Kirchhoff's loops for these guys. Even though we have more components, more voltage sources, doesn't matter. We're still going to follow the same rules. Yes? Yes, because those currents will be going through like that. Okay, so we're going to start. It doesn't matter where you start on your circuit. I just like starting here. So the first thing we run into is the negative 22 volts. The next thing we run into is R1 times IA. The next component we run into is R3 IA. And then the other current, like you guys were saying, is now we have current B. It's coming down through the same resistor as well. So we're going to add that current in our calculations. So plus R3 IB. We come down. We now have R5 times IA equals 0. So again, we're just following the same steps, even though we have more components we're going through. And then while we're here, we might as well put in our values and solve it down so we have one final value. So I'm just going to move this 22 across the equal sign at the beginning because there's nothing else attached to it. I know that voltage is going to move over there. We don't care about what current is there. We don't care what the resistance is. It is a voltage. So we end up with the 3.3K IA plus the 1K IA plus the 1K IB. So that takes care of our R1 IA, which is the 3.3K, R3 IA, and R3 IB here and here. And then the last one is R5, which is 8.2. And that's going to equal 22. Everybody good with that? Okay. Now we combine together all of the IAs and IBs to put them together as one single variable. So we've got a 3.3K, we've got a 1K, and we've got an 8.2K. So we have 12.5K IA plus 1K IB equals 22. This is formula number 1 I need. How many formulas am I going to be looking for? 2, because I have current A and current B. I need a tray right here underneath the bottom of this to stick my calculator. Just get maintenance on that. I'm sure. I believe it. You can super glue it. Huh? We'll get one. Okay, so now that we have our first equation, simplified down as far as we can get, Now we're going to go through and solve for our second equation. We're going to pick any point, and we're going to go in the direction of our loop. Again, we don't care what the induced polarity is. We're just writing down assuming from this loop's point of view. So we end up with, so Kirchhoff's voltage loop B is we have R4 times IB. We have a plus 49 volts. We have a plus R2 times IB. And then we have R3, and again, our two currents are coming together. They're not opposing each other, so we're going to add those two. And so we'll end up with plus R3 IB plus R3 IA. We set that equal to 0. Yes, Dylan?
Does it matter where you start on the circle, just as long as you go the direction?
Just as long as you go the direction of your loop. Yep. You start in one place, finish in one place. Does not matter where you start. These are just the places I like to start. Any questions on how we got that equation? Okay. Now we're going to plug in the values for our resistors. We'll simplify it down to get our second equation. So R4 is 3.3K. I'm going to move the 49 across the equal sign, so that's going to become a negative when we get done. We have R2 is 1.8K times IB. We have R3 is 1K times IB. We have plus 1K IA. And that's going to all equal a negative 49. I'm going to add everything together, that's IBs. Add everything together, that's IAs. I've already moved the non-variable parts over. And I'm going to put this guy in order. So I'm going to kind of do 3 steps at once. So we end up with 1K IA plus 6.1K IB. And that's going to equal negative 49. And that is our second equation. I'll give you guys a chance to write that, get that written down and copy down. You know your beard's too long when you start eating it every day. This is, like I said before, this is the first job I've had. This is the first job I've had that I haven't had to shave to be completely clean shaven for my job. So it's nice. I was on our emergency response team and our medical response team up there. I had to be able to throw on a respirator at a moment's notice. So I had to stay clean shaven. So I didn't get it. The rest of the guys I worked with, they had big old bushy beards, and I wasn't allowed to grow, and it made me sad. So when I got this job, I about threw all my razors away at once. My wife was like, "No."
Is this like a long-term job for you, or are you assuming
I'm assuming that I don't have to change jobs again. Before me was Rossiter. Tim Roster. He's going to be your second semester teacher. Tim Leishman. He's now going to be third semester teacher. Rob was third. Rob is now teaching fourth. Shane. Shane's still sixth. Jaron. Jaron.
Bro, where did the person go?
Huh? They quit. I'm not sure, and I'm not sure exactly who it was, but there was a vacancy there that was being filled by another teacher, and he retired last year. So.
Bro, the circle's still not up. It doesn't equal 0, bro.
The what? Nice. Okay, everybody got those equations? Everybody good? Okay. So now we need to go and we need to solve these. We need to find out what these currents are. So we have 12.5 K IA plus 1 K IB. And if you want to, you could write these numbers out fully. This would be 12,500. This would be 1,000. For simplicity's sake, I'm just going to put in the prefixes. Equals 22. Our second equation is 1 K IA plus 6.1 K IB is equal to negative 49. Now in this instance, I would probably look at one of these to swap around. It's nice we have the 1Ks. That makes it easy because it's just multiplied by 1. Okay? And we need to make one negative. So which one do we want to get rid of, IA or IB? A? Okay. So to get these guys equal in magnitude, opposite polarity, we need to multiply this guy by negative 12.5. Because we're both in kiloohms, we don't have to do anything else with that. So we end up with a negative 12.5 K IA. We take our 6.1 K, we multiply that by 12.5. This is 76.25 KIB, negative. And that's equal to a positive 612.5. Because we have a negative times a negative, that becomes positive. So now, this equation goes away, just so we don't get it confused. And maybe what I'll do is draw a thin line through it. So we can still see it, but we're not worried about it. Now we add these guys together. IAs fall away. We've got a positive and negative of the same magnitude, which is what we're trying to get to. We've got a negative 76,000 plus 1,000. That is going to drop to negative 75.25K times IB is equal to 612.5 plus 22, 634.5. Then we're going to solve for IB. We divide both sides by negative 75.25K. So looking at this, what's the first thing that should be kind of going off in your head? Negative what? It's going to be negative current, but we have a negative resistance. Okay? First thing in your head should be like, wait a minute, resistance by itself cannot be negative. Resistance is always positive. Nope, it doesn't mean we didn't get it wrong. It just means this value is going to come out negative. So we have our loop drawn incorrectly. That's what it's going to come up to be. So when we carry this division out, IB so again, yeah, we get a negative current, which all this is going to mean is that we did our original assumption incorrect for loop B. Now, we take this value and we're going to plug it back into one of our original equations. Either one does not matter. And we want to plug in the negative because all of these equations are assuming the one direction. If we flip it now, we will get the wrong answer. Yes? Okay? So we have 1K IA plus 6.1K IB, which is what we're going to plug in for. And the IB current we had was negative 8.432 milli. Do what? So what does this voltage come out to be? Okay, negative 51.435. 1K IA minus that value is equal to 49. Now we want to get that value to the other side of our equal sign, so we're going to add 51.435 to each side. So 1K so we got 51.435. We're going to subtract out 94 or 49, and we get 2.435. We divide both sides by 1K. Yep.
I got my IB total right, but not my IA. Because I'll do my IA first.
Okay, you probably dropped a negative sign somewhere. You did the IA first?
I did the IA first and got 1.783, and then plugged that into the equation and got negative 8.325 for IB.
So it's
I got IB mostly right.
it would be close. So somewhere along the lines you probably dropped a negative somewhere, which then in the middle of the equation then is going to lose some. Okay. So when we look, we have an IA of 2.435 milliamps positive, and we have a negative of 8.432 milliamps. So that means when we come back to our original circuit, we can put these in, and we get 2.435 milliamps. This one is negative, so we have to change that. and we have 8.432 milliamps.
So how is that gonna work since the current total has to go to R1? Or no, because
There's two power sources.
Ah.
This one we won't be measuring current total because there's no one place that we can measure total current. Essentially, from R3, that is going to give us kind of the net current of these two voltage sources working. And that's where the focus is going to be the answers is across R3. So what current do we have flowing across R1? 2.435. How much do we have flowing across R5? 2.43 milliamps. And that's going to give us polarities in this direction. And now remember, when we measure this, we're going to be measuring from left to right, top to bottom. So when we'd be measuring it, we'd be measuring positive probe here, negative probe here, positive, negative. Or we got the most negative, so we're going to put the black of our probe here. So these values are going to be positive because this is going to be closer to the negative pole. This guy, what about R2? What's the polarity of it? Positive, negative from left to right. Because of this current flow, we're assuming conventional current flow. This guy, positive to negative going that way. What current do we have going through R2 and R4? The 8.4, the IB current. That's the only one that's going through it. Okay? R3, since we had that current flip backwards, we've now corrected it. What current do we have flowing through R3? So we've got that direction, we've got that direction. Polarity is going to be that direction. Okay? So then, when we type in the answer, remember we read top to bottom, left to right when we measure polarity. So when we put in our voltmeter, oops, let me make that a little bigger. That's how we'll hook up our leads, and it's going to show negative. Because our voltmeter, we're reading top to bottom. So the positive up here, negative down here, opposite polarities, we're going to show a negative voltage. We would write it down as negative because it's going to be in terms of how we're going to measure it.
So the reference point would be in Y.
Yes. Yep. So it also gives us in the description on the quiz. I'll show you. Right here. Note, VR2 polarity seen from top to bottom. Red lead on the top, black lead on the bottom. Okay. Any questions about that?
Isn't it also like because it's in parallel with that voltage source, it follow that same polarity?
It will to some extent because you have both of them feeding into it now. So now you have multiple circuits, multiple power sources feeding into everything. Yep, they're just superimposed over each other. And then, do what? Like I said, I like this better than Thevenin. Do what? Two channels? Yeah. Mm-hmm. Yep, and you'll just plug them in and go. Put them in basically in series is what they're doing. Yes. You have one on your bench. So, in the wild. A lot of times you'll have two different feeds coming in. You'll have them generated from two different power sources. Sometimes they could even be like a sensor, like a temperature sensor. So you have one power source that you regulate. The other one is going to be like a temperature sensor that you could use, and then measuring across this resistor. Like if you wanted to use it somehow, I don't know why you would, but then your other supply would come from a temp probe. So the hotter it gets, the more voltage it's going to have across its line. It's another way to analyze a circuit. Sometimes that's all you have is just essentially a voltage source. You know how much voltage is coming out of these two terminals, like off of a generator or things like that. A lot of times it's just a way to kind of look and analyze the circuits and understand how mesh works.
So it's not necessarily something you're gonna see a lot, but it's just the math.
It's the math behind it. It's showing just putting more crap really inside the circuit. How do I treat it? Just to kind of get you guys to not be completely scared and overwhelmed of some of the stuff when it comes up. Okay, any questions about these guys? Okay, like I said, the biggest part of these is just understanding, and we can put these power supplies in however way we want. It does not matter. We're going to treat it the exact same. Draw out your loops, create your Kirchhoff's voltage equations, and then solve them down. Get them to a point where you have the variables isolated and the non-variables on the other side of the equal sign, and then you'll use simultaneous equations to solve for them. No. That's the idea. The stuff. It's because these are actual hands-on examples of how to use this math. Just like at the end of the week. So this one's going to kind of follow the backwards plan. We're going to do our theory first. We're going to do the math later. End of the week, we're going to be getting into logarithms. Logarithms are not going to make sense until we get into the next week with DC, and then when we start getting into AC signals. Don't worry. Like I said, don't worry, guys. There's a reason we teach you guys in these orders, because we're teaching you the math behind it. Then we'll teach you how we use it. The biggest thing with logs is they allow us to remove an exponent and solve for things in an exponent, which we're going to have to. There's going to be times with some of the equations we're going to work on that's going to be you're solving for a value in the exponent, and logs is the only way to get that exponent in a way where you can manipulate it. So like I said, with that, that's what we're going to do. Okay, for homework tonight, I want you guys to look at this.
Yes.
Yep. Our Wheatstone bridge circuits. It'll be in the lab next week.
Which week are we on in lab?
We are on, so you're on week, so it's week 6 is where we're at, but you're working on week 5 material.
Oh, from theory.
We did both of, yeah, we're going to do it in last week and this week, and then possibly the week after. This is a Wheatstone bridge. Okay. So there's your circuit. There's your loops. Remember, we're looking at the space in between the circuits to create our loops. We have one loop here, one loop here, one loop here. We're going to end up with 3 equations. We're going to use simultaneous equations to solve 3 equations at the same time. Take a look at this. Come back with questions tomorrow about it. If you get it, great. If you don't, like I said, we're going to go through this. But I want you guys to at least look at it, however short, long it is you look at it. Because let's be honest, I know you guys are probably going to go home and not look at this. I didn't when I was in class, but okay. We will pick up here tomorrow.